My talk is based on a joint work with Alexander Ilyich Nazarov, which was published as a preprint and now to appear in записки научных семинаров. The motivation for this work was a paper by Nikitin and Henze Henze and Nikitin, containing several goodness of fit tests based on integrated and centered processes, just in spirit of the talk of Professor Nazarov somehow. So two operations to improve somehow, to look for new statistical procedure, integrating and centering in different order. And as usual, in the spirit of one of the main direction of Nikitin's works, the Bahadur efficiency was found, and the following problem was posed to find the alternatives for which the statistics would be locally optimal in spirit of Bahadur. This is the area which was we can say that it was founded by Professor Nikitin, finding the alternatives for which the given test would be locally optimal in Bahadur sense. And it turned out that for one of the test statistics, something goes wrong. It means that the corresponding variational problem was solved, but the solution didn't lead to any probabilistic result. So Professor Nazarov noticed that there was also another case of such behavior of the test statistics. You can find its large deviation, you can find the formulas for the exact slope and for local Bahadur optimality, for local Bahadur efficiency, and you can write out a variational problem, but you cannot. You can find the solution, and it is not probabilistic. It doesn't lead to a family of distributions, just one distribution. So no distribution corresponds to this problem. And from this point, a question arises: which maximal Bahadur efficiency you can obtain? So it's obvious from what I've said that you can't obtain the efficiency 1. So what is the maximal available efficiency of a test? And let's return to the problem setting. So the usual beginning of such papers for xj, the independent observation of a random variable having a continuum distribution function, we are testing a simple hypothesis f exactly equal to f null, fully specified, against the alternative non-parametric alternative of the sort f is not equal to f null. And we apply, we construct an empirical process, a usual empirical process, and we transform it in some way. For the definition of the measure of the efficiency, I refer to Nikitin's book, which was already mentioned today. And I think that in this room almost anybody knows the setting. And then we find the asymptotics of the form as a local asymptotic, the square term as the first term is 0, so usually the term has the form of some b, which is called local Bahadar index. And b is defined in terms of the alternative. So it's well known that we bound the exact Bahadar slope and hence the approximate Bahadar slope by the twice the Kalbach-Leiber information by the Bahadar-Rogovaceri theorem. So we are looking for the statistics for which for the alternatives for which the statistic is locally optimal in Bahadar sense. The abbreviation will be LAO. And among all alternatives, for instance, parametric alternatives, we choose shift alternatives, for which the problem of finding the efficiency becomes a problem of special sort. If we have a sequence of alternatives, a family of alternatives depending on theta, then we to describe the family of locally of the alternatives for local Bahadar optimality, we introduce, in fact, you can. I refer to Nikitin's book for the definitions. We describe the family in terms of so-called leading functions. And it was shown that by Nikitin that under some regularity conditions, the corresponding distribution function is a solution of such a differential equation. And for a shift family, which is described by this simple formula, this equation may be rewritten this way. So it's easy to see just by taking a derivative by theta. And we can see that in this case, the leading function has to be positive on the interval from 0 to 1. In fact, this transformation is made, in fact, it is a Smirnov transformation. reduce the problem of goodness of fit testing in a usual way to the testing of a hypothesis that f null is just equal to x on the interval from 0 to 1, and for this purpose we make a Smirnov transform, and after that we come to this formula. So we can see that for shift alternative, this optimality condition requires that this leading function should be positive on the interval from 0 to 1. And usually for a huge amount of tests, it's the case. One can find such family of leading functions, non-empty mostly. But in the case I want to tell about, this leading function, the solution of the differential equation, turns out to be sign changing. It means that it is not a Smirnov transform of any distribution function. So this solution, it exists, but it's not. It has no probabilistic meaning. Okay. Let's set a problem. What is the maximal available local asymptotic efficiency of such statistics for the shift alternative? I want to say that the fact that the maximal, efficiency 1 is never attained for shift alternatives, it doesn't mean that it isn't attained at all. We don't know, in fact. Maybe for some other families of alternatives, maybe for scale or some, I don't know, lemon or maybe something else. But for the shift, there is another problem. So we modify the problem in the following way. We are maximizing the corresponding functional j of u on the set of non-negative functions from the unit ball in Sobolev space. So non-negative functions can lead to some probabilistic solutions. And from the said above, it follows that the corresponding efficiency can be 1. It is necessarily less than 1. Notice that the maximizing function turns 0 in the interior points of in some interior points of the interval 0, 1, and hence it doesn't lead to a distribution with a continuous distribution function. And from the original assumptions in the problem, we suppose that we need a continuous distribution function. But in our case, for example, if maximizer has the form, we can see which form it has in reality. For example, if it has the form of, I don't know, something like this, we shall see that it's quite another thing, but why not? It doesn't still lead to a continuous distribution function, continuous distribution function for the alternative, but at the same time we can approximate approximate the leading function in a way that we can obtain any efficiency close to the maximal available efficiency. And for example, for the function obtained as a solution of the differential equation, obviously we can't approximate it in such a way. So this is not our case. So we can approximate the supposed the maximal available efficiency. We can approximate it up to any positive epsilon. And another problem of such a sort, when we can't find a solution having a probabilistic sense, was studied in the thesis, PhD thesis of Podkorytova. It was also a statistics based on transformation of the empirical process, and it also led to some variational problem which didn't have any purely positive solution. So now let's forget about the statistical setting and pass to the variational problem, which was the main interest in this work. Let us pose the variational problem. We are searching for the maximum in the extremal problem. Let us return. Sorry, I'm not very familiar with this. Спасибо. Окей. Тут еще глазок есть, он впереди. We are dealing with a variational problem. We are maximizing the functional. For the Nikitin-Henze statistics, it is the functional of this sort. And for the Podkorytova statistics, it will be described later. Under a condition, the following condition with fixed points, u equal to 0 and at the end points of the interval, unit interval. And let us find for the, let us look for the solutions with a restriction, with a new restriction. The restriction is of the form U non-negative. And we describe, we are writing the conditions for the necessary condition of maximum for all Sobolev variations such that the condition, this condition is satisfied. And we are searching for the solution of this equation. We have in here F1, which is defined by this formula. And then we proceed in several steps. First off, we prove that this thing is non-positive in the sense of distributions. So it's a measure with the sign, and its singular component is non-positive. Then we prove that the set, a set where U is strictly positive is at most countable union of intervals. And one can look at it. Here it is a finite number of intervals, and it's just reminds of the real result. So at any of these intervals, we have that, in fact, the second derivative is lambda times f1, and thus the support of the singular component of the measure second derivative of U is contained in a set where U equals to 0. And then we prove that U second derivative has no singular component at all, that it's just an ordinary function. And by this reason, the first derivative is continuous on the unit interval, and therefore, at the ends of each interval, let me make a correction. At the ends of each interval, we have the first derivative equal to 0, except maybe the points 0 and 1. And then we prove that first we said that at most countable union of intervals is possible as a support of the measure, but now we see that not countable, but only a finite number of intervals is possible. And note that the set where where U vanishes is non-empty. Otherwise, we would have a probabilistic solution for the original problem in Henze-Nikitin, and it was shown in Henze-Nikitin that it is impossible. So we are looking for a function having some intervals where the function vanishes. And after some reasoning with the second derivatives, we show that in fact remain only 3 variants for the equation on the second derivative. In fact, 2 of them are equivalent by symmetry, and the third variant, that means that function U satisfies to some differential equation at an interval starting from 0 up to some x null. That is, instead of this picture, we can say something like that. Or or something like that. And we can show that the third variant with two separated intervals, that is the variant of the sort is unprofitable. Okay. No, sorry. Is unprofitable as we can improve it by, for example, by cutting half of it and how to say? Stretching, inflating, stretching. Okay. Okay. So only this variant or the symmetric one, which is equivalent, remain. And now we come to the equation we are going to solve. So we to pose a differential equation, to set a differential equation, we differentiate the initial equation twice, and here is the problem we are solving. And there will be quite a lot of computation for the solution. So this equation has to hold on an interval up to from 0 up to x null, and we have I've written it twice. Okay, and we find a general solution of the form. There are sines and cosines, ordinary and hyperbolic, so it's obvious. And also plus a constant, and so it depends on 5 constants. And we introduce for convenience, for simplicity, we introduce, as we deal with the fourth derivative, we introduce k, which is for in such a way that its fourth power is equal to lambda. And we also have 5 Кого?
6 conditions.
6 conditions. Okay, so we have 6, yes, 6, because we have 5 constant and also k. Okay, it has to, the solution should satisfy 2 boundary conditions at 0, 2 boundary conditions at x null, and 2 matching conditions in a way that it has derivatives. And this leads to the following system for, it's a nonlinear system for parameters k and x null. So we find all the constants and except for x null and k, and we exclude the extra constants, and we get such a system of equations with the solution. And now the solution is determined up to a multiplicative constant. And we finally can see that the graph of the corresponding maximizing function u is given by this figure. And finally, we find the x. It was purely computation. We find the solution x null equal to 0 point and so on, and corresponding k hat equal to 5 and so on. Now we come to this maximizing function, the solution, which maximizes the functional under given restrictions. And finally, we find the optimal local index for the available local asymptotic efficiency of the test statistics under the shift alternative. It is, we compare this local index with the optimal local index, and we see that the alternative is about 67% from the potentially optimal. But in our case, the maximal available local asymptotic efficiency. So we cannot test the shift hypothesis with these statistics, with the use of these statistics, better than at 67% from the optimum. And now we proceed to Podkaritova's statistics. One of it, yes. For the one for which there is no optimal, which doesn't attain its the maximal unit efficiency at any shift alternative. So this is the statistics based on the transformed empirical process, based on the Duval's transformation of the empirical process. And we consider the case of the case of p equal to 2 infinity, and we formulate the extremal problem, and once again we reformulate it in a way that the solution should be positive. And first of all, we find, as it is usual procedure for supremum type statistics, first we find the maximum for the auxiliary functional of this sort, because our test statistics is max type statistics, and then we maximize, we fix x star, and then we maximize the result in this x star. So we once again come to a set of equations not only for lambda, but also for x star, and also for some x0 defining the interval of non-vanishing. So it is this problem partly reminds the previous one, but as it is max type statistics, there are some differences. So we formulate the extremal problem. We derive the necessary condition of maximum. For all variations from some Sobolev space. And here we see a distribution F2. It's a measure of the sort. It is derived from the form of the test statistics. And we introduce the notation V, which is a well-known Khmaladze transform of the function U. And the difference here is that in this case, we have a we have conditions on the second derivative of U, and condition at the point x0. And now we solve the corresponding differential equations on from 0 to x null, and then we maximize the solution. In fact, we maximize the inverse lambda in x star. So our solution should depend on x star, and then we maximize it on x star. And finally, the computational part is finding the global maximum. We show that it exists. It is attained at some point which is described here. And we can see that comparing the optimal local index from Karitova's thesis with the maximum of our functional, we see that the available efficiency, maximal available efficiency, is about 22%. So we compare this value with this one.
What does it mean, 82% from the optimal? How does it sound in Russian?
From чего?
По-русски. Как по-русски? Что ты хочешь сказать? 82% from the optimal.
From the optimal, ну, это оптимально, это единица. Единица не достигается. А это 82, да. 82 достигается, в предыдущих 67 достигалось.
I thought it was just 18%, even 82% from the optimal. I thought it means 18%, but it means 82%.
Efficiency is 82%.
Hmm?
Efficiency is 82%.
Yes.
Okay,
Yes. And not more.
I got it, thank you.
Hmm?
I got it.
Th- Okay, thank you.
Well,
Mhm.
okay, let's stand speaker.
Такой вопрос. А вы как эти те экстремальные задачи, какие вы пишете, аналогичны задачам, которые возникают при изучении эффективности в зоне вероятности умеренных уклонений? Точности. Более того, можно показать, что локальная эффективность по покатугу
Мгм.
является частным случаем эффективности локальных для вероятности умеренных уклонений. Ну, такие всякие результаты были у
Мгм.
трех товарищей, тогда как-то это дело обобщалось еще. Ну и тогда получается, что решение этой ваших экстремальных задач не обязательно должно быть положительно, а только оно должно быть ограничено.
А это почему?
Нет, ну, то есть в другой ситуации может быть другая, но в этой-то все-таки никуда не деться, должно быть положительно.
Я не знаю. Получается вот такая вот история.
То есть такие же задачи получаются из других соображений. Я правильно понимаю?
То же самое информационное количество Фишера, грубо говоря, минимизируется по направлению.
Ну да.
Нет,
Вот там, вот и, но поскольку там у нас минимизируется f,
Нет,
минус
подождите,
f
тут-
нулевое,
I'm sorry, там информационное количество Фишера здесь как раз фиксировано. Мы сравниваем отношения.
можно
с-
решать
Двойственную задачу.
двойственную задачу. Мы фиксируем уровень и минимизируем информационное количество Фишера.
Ну, в общем, здесь, ну да.
Вот. И тогда ответ получается в виде функции f, которая есть гипотеза плюс возмущение. Ну, bn плюс возмущение, где bn стремится к нулю.
Ну, это прямая задача. Здесь она, в общем, тоже решалась, только не Фишер, а Кулбек-Лейблер.
Я понимаю, но это ситуация такая, что когда вы переходите к локальной эффективности,
Угу.
ваш Кулбек-Лейблер порождается
Ну да, да,
Фишером.
да.
Вот об этом и речь.
Ну да.
И вы по существу, так, когда говорите о локальной эффективности, то по существу вы заменяете большие уклонения умеренными уклонениями.
Ну, можно и так сказать. Локальный, да.
Ну, и для локальной эффективности, когда вы находите решение, вот эту самую функцию u, то она у вас получается, тут ваше решение, я не знаю, не помню, как оно там обозначается, f, то это ваше f есть гипотеза плюс возмущение, вот умноженное на решение. Ну, некая константа.
Мгм. И там тоже есть это ограничение?
Там одно только ограничение, чтобы это возмущение было ограничено по мудрости.
Мгм. Мгм.
Ну и в результате этого вы находите решение. Ну, это обрезание снизу, которое вы делаете, вы можете все более увеличивать,
Мгм.
когда вы, так сказать, приближаете к гипотезу, как альтернативу.
Я думаю, что все-таки дело же все в том, что мы рассматривали специфическую гипотезу сдвига. Может быть, не для сдвига что-то другое будет. Может, нам не нужно будет обрезать снизу, потому что,
даже
она
наверняка
колеблется.
Для,
Да.
для растяжения там этого эффекта.
Ну, понимаете, сдвиг ваш, опять-таки, аппроксимируется линейной моделью. Единица плюс там это самое.
Да, да. И в этом случае не возникает этой проблемы, потому что эта вариация, она не сильно портит все.
Ну вот да, ну вот я из этого и говорю, что
Да.
когда линейные проблемы вы аппроксимируете, то все хорошо получается.
Ну,
Вот
конечно,
я не знаю, вот я просто
конечно.
так обожаю.
Да, но здесь специфическая задача именно для сдвига.
Нет, ну хорошо.
То есть для нее всё плохо.
Если вы пришлете вот ссылку на то, что вы сказали, прекрасно, мы посмотрим.
Ну, спасибо, да.
Пишу 3 ссылки.
Ну, хорошо.
Спасибо, просто умеренное уклонение тут я ничего не знаю, и поэтому, да.
Посмотрим, так сказать, как это связано и можно ли из этого что-то извлечь.
Ну хорошо.
Спасибо.
Ну ладно, вы мне
Спасибо.
Еще вопросы или комментарии?
I wondered if this procedure can be generalized to the case of the family of local scale alternatives.
Maybe if you have an example for which
No, I'm just asking for those two
Yes.
particular tests.
I think that
If the set of alternatives is not the set of shift
yes,
alternatives.
yes, because we just rewrite the parametric family. We find in fact, in Nikitin's book, he says that the other alternatives, such as scale alternative, can be easily reduced to rewritten. Just we replace x by log x or something like this. Yeah.
This is if you consider scale alternative with
Positive how?
distribution supported on the right
Yes, yes,
half
yes.
line. Yeah. But if you have the distribution supported on the whole line and consider scale alternative, this effect is not. It is not the case.
That's what I am asking.
Yeah.
In case, for example, testing normality.
Yeah, because before zero you have negative derivative, after zero you have positive derivative, and just this solution will be okay with one changing of sign.
In fact, in simple words, when you have a shift alternative, taking off absolute value or square, I think it only worsens the effect because you have for the initial function, the distribution function, you have such form, and for the shift you have such a form. So the differences it never change its sign. So no reason to take absolute value or something like this. Maybe it's one of the and moreover centering and integrated process. Maybe it becomes worse.
Okay, more questions? Let's thank the speaker again.
Thank you.